Hi guys, this is video 4-1, the first video of Unit 4 for Tuesday, November 29th. That's when you should watch it. And there's no homework that is going to correspond to it. And so the first thing about this lesson is talking about what a critical point is. So here, critical points. And I'd like you to write this down also that I wrote down here, but you could do that in a moment. Let me read this first. The critical points on a graph are where the derivative or slope is 0 or undefined. They occur wherever you see, and then I have these following things. And the reason why we're going to be focusing on critical points a lot this unit is because, and please write this down, they are the points where a potential important change occurs. Now I say potential because just because something's a critical point doesn't mean it's going to represent a place where a important change occurs. And you may be asking, what do I even mean by important? And I'll talk about that later. Okay, so relative maximums or minimums. Relative maximums and minimums are different than absolute maximums or minimums. We'll talk about those later in the unit. A relative max or min is just the highest point. It's the highest point within a neighborhood of points around it. Okay, so like this point here has the highest y value within this neighborhood of y values around it. So that's why that's a relative max or min. An absolute max or min would be the highest overall or lowest overall, but we are not going to talk about that yet. So this here would be a relative minimum because this point here, it has the lowest y value within this neighborhood of y values around it. That would be a relative maximum. Notice it's lower than this relative maximum, but it's because we're not talking about absolute maxes, which would be highest overall. Just a relative max means within a certain neighborhood it has the highest y value. And then down here would be a relative minimum because even though it's higher than this minimum, it's a relative minimum because it's minimum, has the minimum y value with respect to the other points around it. Okay, so at these points, guys, the reason why these points would correspond to, or they would be critical points, or their x values would be critical points, is because that's where the derivative is 0. Okay, like if I take, and I'm going to be using this transparency a lot, so if you have it on you, you should maybe use it with me. But the derivative there, the slope is 0. The slope there is 0. Same thing for the other ones. So that's why those would be critical points. Now, some inflection points. We will talk later more about what an inflection point is, but these would be examples of inflection points. And I actually, guys, let's write this down. Some inflection points. All right, these I read the other day are called saddle points. Okay, so definitely saddle points. And it kind of looks like the saddle, I guess, that you would like ride a horse with. So like right there, that would be a saddle point because the derivative is 0 there. Okay, it has to go, it's like, negative, but less steep, less steep, less steep, less and less steep till it hits 0, and then it gets like more steep again. And then that would be another saddle point. Okay, holes or breaks. Obviously, the slopes of the tangent line here are not the same as like the slopes of the tangent line getting closer and closer to that point there. So since the derivatives don't agree, then the derivative would not exist. It would be undefined. Okay, an asymptote. Guys, here the function's not even defined, so of course the derivative is not defined here. And then vertical tangents. Vertical tangents have an undefined slope, so the derivative would be undefined. Here's an example. This almost looks like a saddle point, but it's not, because at a saddle point, the derivative would be 0. This is almost like a flipped or rotated saddle point, and that would give us an undefined slope there. Okay, so the x-coordinate of this point would be a critical point. And then sharp corners. If you have any sharp corners, guys, the derivative is not defined there. Okay, and this is why. All right, the derivative, so to this side of the sharp corner, the graph is linear. So, the slope of the tangent line would be the same as the slope of the graph. So there's that derivative. Whatever that slope is would be that derivative. And then on the other side, remember the limit definition of the derivative, guys? A derivative is a limit. It's the limit where you take this, so I'm going to look at this secant line that is going through this point that I'm considering the derivative at, and it goes through this point on the graph there. And what the derivative is, the limit definition just gives you a limit of all of these secant lines, all right, and they get closer as we take points on the graph that are closer and closer to the point of tangency that we're looking at. The secant lines become the tangent line, and as you can see, this slope is not agreeing with the limit of these slopes at all. Okay, so just like with the limit won't exist if it doesn't agree from both sides, same with the derivative. The derivative is not going to exist if it doesn't agree from both sides, if you're not approaching the same slope from both sides. So just to summarize here, guys, off to the side, let's say here, these were critical points. Why? Because the slope was 0. Okay, the x values that correspond to these points are critical points because, again, the slope is 0. But then for all of the rest, those x values were critical points. The x values corresponding to, what we looked at were critical points, not because the slope was 0, but because the slope was undefined. So maybe I'm just going to go like one of those. That doesn't look very good, but M is undefined. Okay, so we'll talk more about critical points in the future. I'll talk about them a little bit on the next page. But that brings us to sketching derivative graphs, okay? So I am giving you the graph of a function, and we're going to sketch the graph of the derivative. And tomorrow for partner problems, you'll do some of this. All right, and I will have extra of these tomorrow in class. So this is the graph of y equals x squared. And already, guys, I don't want you to completely rely on the derivative rules to figure out what the graph would look like. I want you more to think about what's happening with the graph. But it won't hurt to draw on prior knowledge. What is the derivative of x? Oh, yeah, I'll say it now. What's the derivative of x squared? 2x. That's a line. So the derivative of a parabola or of a quadratic function is going to be a linear function. So I already know I'm going to have a line over there, but just kind of let go of that, please. Okay, let go of the fact that you know the derivative of this is 2x and that you know what that line looks like. Let it go, because that's not going to help you in the future. So what I want you to focus on is this instead. So right now, before we get going, why don't you draw 4, axes, and then just draw 4, just indicate 4 x values to the left and right of the origin. Do it on every graph here, guys. So I'll give you a moment to do that. Or actually, just pause this. Okay, pause the video to do that. I'll keep going. Yeah, so pause the video right now and do all that. And then, okay, so now that the video is unpaused, because hopefully you're done doing that, I'm gonna put my transparency up to the graph, and I'm gonna think about the slope. I don't have any, well, other than the fact that I know this is y equals x squared. Let's suppose that I maybe scaled this differently, or, don't rely on numbers here. So let's say we don't really know what that slope is, but what can we say about it? We can say, number one, that the tangent line is decreasing, right? So that means that the slope is negative. And the tangent line is also steep. So we know that the slope is a big negative, okay? So a decreasing steep tangent line means a negative big slope. Okay, so I'll say it the other way. So a steep decreasing tangent means a big negative slope. Steep decreasing tangent line means a big negative slope. So over here, at this x coordinate, I know I'm going to have a big negative number. Okay, now let's move along the graph. Let's look at this next tangent line. All right, it's not as steep. but it's still negative. So not as steep. Yeah, so not as steep, still, it's not as steep, but it's still decreasing. So it's not as big a negative slope. So it's going to be like this. And I'm cheating a little bit because I know that this is going to be a line, and I know it's going to go through the origin because the derivative of that is 2x. So I'm just making sure that this is going to come out looking nice. So there's the next value of the slope. So we're plotting, the y values here are the slopes of these tangent lines. Okay, next, still decreasing, not as steep, so a negative slope that is not as big negative as the others. Okay, so like that. All right, so guys, I think you get the idea. So we're gonna have some linear action because every time I move the tangent line closer and closer to the origin, it's still negative, but it's not as steep. Okay, so it's still decreasing, but not as steep. So still negative, but not as big. Okay, and then finally here, guys, this is a relative minimum right there. Okay. And the tangent line there, the slope of the tangent line there is 0. So at the x value 0, the slope of the tangent line is 0. So that'll be another point. So I'll have like all of these slopes there. And now let's see what happens on the other side of it. I'll just go a teensy bit to the right. That is an increasing line now. So, okay, so this was a critical point. Remember, I said earlier, points where a potential important change occurs. This is an example of an important change, guys. From a decreasing tangent to an increasing tangent, that's an important change. Okay, and the reason why, and we'll talk more about this in the future, is because it would indicate a relative minimum. Okay, so, and if I'm going too slow, guys, please speed this up. I don't want to lose anybody here. This is important. So I look at this slope. The slope here is positive, but it's not really a big positive because it's not that steep. So it'll be like, maybe like there. Still positive, getting more steep. Still positive, getting more steep. I feel like I'm kind of like messing up with these hash marks. But, so there you have it, guys. It is, all right, and that's not really perfect, but. So I'm cheating here because I know that the derivatives align because I know x squared. Okay, but that's how you want to be thinking of it, guys. Imagine the tangent line, imagine its slope, and its slope at whatever x value is the y value of the derivative graph at that x value. Okay, so now this one here, x to the third. So I'm going to do the same exact thing. Oh, and it looks like we have a saddle point here. Let's see. So there's the tangent line, tangent line, tangent line, tangent line. Yep, that looks like close enough to a saddle point. I wanted it to be one. So I'm going to go right ahead, and because at this x value 0, the slope of the tangent line is 0. So over here in my derivative graph, at the x value 0, the slope is 0, so that'll be the y coordinate right there. So I just did that right away. Okay, so here we go. Now think about what is happening to the slope of that tangent line as we move along this section. Okay, so starting here, I have a positive slope, and it's pretty steep, the tangent line, so that's a big positive. So I've got a big positive like out here. Okay, like a big positive. And as I move along the graph, it's still positive, but it's less steep now. Okay, so still positive, but less steep. And as I move along the graph, it continues to be still positive, but less steep. Okay, so still positive, but less steep, still positive, but less steep, until we get to that saddle point where it's 0. So guys, if it's still positive but getting less and less steep, the slopes, the y values over here are the slopes of the tangent line. So the slopes would be getting, lower and lower. So it's going to be like this. And maybe some of you have already realized this, or actually I'll say that later. Okay, so then on the other side of that saddle point, which would be a critical point, the slopes are still positive. So we don't really have a change there from positive to negative slopes. But the slopes are still positive, but not so steep right there. Okay, so still positive, but not so steep. Still positive, but steeper. Still positive, but steeper. So you'll see that it's going to look like that. And maybe some of you already have thought about this, but what's the derivative of x cubed? 3x squared. So that would be a quadratic. So the graphs that we're ending up with by just, using our tangent lines and thinking about the slope visually, those are in line with what we already know about the derivative. Okay, guys, almost done. Now this one here, where do I have a critical point? I'm going to think about that first. And sharp corners, any sharp corners, guys, the derivative is undefined there. So this is going to be a critical point right there because the derivative is undefined because that's a sharp corner. And critical points are important because they are points where a potential important change occurs. Okay, so let's look here. This is the graph of the absolute value of x. And to this side of that critical point where the derivative is undefined, the derivative, the slope of the tangent line is the same as the slope of the graph because it is linear. And let's say that that's maybe like the slope here, maybe it's -1. All right, but I'm not going to actually put -1 there. So, but I'll just put like a hatch mark there. Well, and I'm going to do the derivative here, then I'll think backwards. What's the derivative at this point right here? It's undefined because these derivatives aren't matching. This slope does not match with that slope at all. Okay, they're very, very different. So I'll just do an open circle. And then this slope is constant. It's not changing. So the slope here, let's say like it's -1 or something or whatever this y value is, it's just going to be a constant slope. All right, the slope at this point is the same as the slope at that point, same as the slope at that point, same as the slope at that point, so you'll get a constant function. And then on the other side, we have a similar thing going on, but it's positive. The slope is positive. So still the derivative is undefined there. Okay, so I'll just have an open circle and then to the right. I'm still a little sick, guys. I hope I'm doing a good job, sorry. Now, this last one, and I hope if I was going too slow that you speeded this up. So this very last one, it's 1 over x. And, all right, so let's take a look. So starting, we'll go from left to right. So starting here, this is a negative slope because it's a decreasing tangent line. And it is not very steep at all. Okay, so like out here at this x value, it'll be negative, but not a very big negative number at all. Okay, and then as I move along, I'm remaining negative, I'm staying negative, but I'm getting more steep. So bigger negatives, bigger negatives, bigger negatives, and they aren't just getting bigger; they're really getting bigger fast. Okay, so. You see in the original graph, this is an asymptote. It turns out same with the derivative graph. This is going to be an asymptote because the slopes just are getting so steep, like infinitely steep. So that will be an asymptote there. Now on the other side, we're starting here, I'm moving from left to right, with a very, very steep negative slope. Okay, so a very steep negative slope right there. So I'm going to be like, I'll be like way down there. And then a less steep negative slope. And then a less steep negative slope. So guys, we're going to have the same action because we're just getting a less steep negative slope, but always negative. All right, it's still negative, but it's getting less and less and less steep. Okay, so there's that derivative graph. This was a very long video, guys. I apologize for that. But there is no homework. So there's the consolation. And I will definitely see you tomorrow. Okay, bye-bye.